So when we described the kinetic theory, what we said was that the particle goes through basically unabated, hits the wall, comes back over here, hits the wall, comes back over here, hits the wall. So the time that it took for that to happen was on average just twice the length divided by the x portion of the velocity. Well, this isn't quite necessarily true. That's an oversimplification of what's actually happening, because there are other particles in here. They are going to all be moving in different directions, which means at some points in time, some of these particles will be colliding with each other. So basically, what will happen is, if I had a particle here, say again mass m, moving in this direction with a velocity v, it will move in a straight line until eventually, let's say where there's another particle coming in this direction, the velocity, I don't know what's called that, v prime, so eventually these two are going to hit at this particular location, at which point in time this one may bounce off, say, in this direction, and now it's going to move this way with, again, some sort of velocity, where it's going to keep moving in a straight line again. So, what we want to know then is, well, what then is the average distance one of these particles is going to travel before it ends up making a collision? Now, one thing we can say is what? The number of collisions it's going to make is going to go up if the density of the particles, that's the number of particles per unit volume, goes up, which means that that distance it's going to travel then is going to get much shorter. So, again, what we want to know is, if I'm looking at this particle here with mass m, let's say this thing has a radius of r, so that it has a diameter of d, so let me just call this diameter of d, and let's say this thing is moving in this direction with a velocity of v, and inside of here I'm going to put other copies of this guy, say somewhere around like here. So again, what we want to know then is, what is the average distance this guy is going to travel? Let's say to here, I'm going to call this lambda, what's the average distance this guy is going to travel between collisions? Okay, so again, on average. So this thing is what's known as the mean free path. So the mean free path then is the average distance that this guy is going to travel before it makes successive collisions. Now, to do this, we're going to make a couple assumptions. So the first assumption we're going to do, just to simplify our lives, is we're going to say that the only particle moving in this is the one single particle we're going to look at. So all these other ones are frozen in space. That's it. Also, we're going to say is, let me take the size of this guy and make him twice the size, while I'm simultaneously making all of these smaller. So basically what I'm going to do is I'm going to turn all of these other guys into two-point masses, and I'm going to double the size of this one, so it has basically a radius which is now equal to its diameter. So basically all I'm doing then is we're going to redraw this. So now what's going to happen is, now we're going to have this guy, whose radius is now equal to the original diameter, moving in this direction then with a velocity v, where again this velocity is got to be the same. And now I'm going to put a whole bunch of little point masses which are not moving throughout this entire space. Okay. Now, somebody's laughing. Anyways, at the end we're going to relax the fact that we're going to allow these guys to actually go back to moving at the right speed, and we're going to go back to the fact that this thing has a radius r, so a diameter d, and make all these guys have the same thing. But for now we're just going to look at this guy. So basically, we're then going to define the mean free path then as what? So this is going to be equal to the length of the path divided then by the number of collisions. So we want to know then, how many collisions is this thing going to make in a given amount of time of, say, delta t. So let's say this thing is moving here, we're going to let it move for a time of delta t, and we want to know how many collisions would this thing make at a time of delta t. Well, since this thing is moving with an average velocity, this thing is then going to move, say, some distance here in that time frame of delta t. Okay. Since this is my diameter here, this is my diameter here, then the distance this thing is going to move across here, L, is then equal to simply the velocity times the change in time. So that's actually the length of the path. But as this thing moves, then it's going to sweep out a volume, right? So basically here it's sweeping out this entire volume. where the volume in this case then is going to be equal to the cross-sectional area, which is that of a circle, so simply pi r squared, times the length, so this is going to be then pi d squared times v times delta t. Now, here we can then say the number of collisions is then going to be equal to the number of molecules per unit volume, so this is the density of the particles, times then the volume that this thing sweeps out. Right? So the number of collisions then is going to be equal to the number of particles per unit volume times the volume, where this is the volume at which it sweeps out. So this is the volume swept. So it's going to be equal to then the number of molecules divided by the volume. So again, number per unit volume, so this is the density, times then pi times v squared times the velocity times the change in time. So we'll put that into our mean free path. This is then going to be equal to simply v times delta t divided by pi d squared times v times delta t times n over delta v. So this v is going to cancel this one, delta t's are going to cancel. So finally what we can say then is what? The mean free path, again, which is the average distance between two successive collisions, is then simply going to be equal to 1 over pi times the diameter squared times the number of molecules per unit volume. Now again, here we're assuming that all of my particles are stationary. They all have a diameter equal to 0. They're all simply point masses. But now, if we relax that, go back to our original situation where all these guys can actually be moving, turns out in this case, by relaxing that, we only pick up an extra factor of square root of 2. So in this case, we find that our mean free path is then equal to 1 over the square root of 2 times pi times d squared times the number per unit volume. So again, as we said, in this case what we know is that, what? Again, as the density goes up, the distance should actually go down, and then as the density goes down, that distance should actually go up. And again, the reason for that is if there's more molecules per unit area, then that means the chance of making a collision is actually going to increase, which means that average distance between collisions should, in that case, then go down, as opposed to if I have a very low density. In that case, we should expect the number should actually go up. So let's do a quick example. So in this case, let's say we have a particle accelerator. So in this case, we have a certain particle accelerator with protons travel around a circular path of some diameter. We don't have to worry about any of that. Whose residual gas is at a temperature. So here T is equal to 295 Kelvin. And it has a pressure, which is then equal to 1 times 10 to the minus 6 torr. So this is a very, very, very low pressure. So this is basically a vacuum type situation. So first thing I want to know is calculate the number of gas molecules per cubic centimeter. So for part A, first thing I want to know is N over V. What is this equal to? So what is the density? Again, per cubic centimeter. We'll do both for meter and then centimeter. And then finally for part B, wants to know what is the mean free path if the diameter is equal to. So what is lambda equal to if the diameter is equal to 2 times 10 to the minus 8 centimeters. All right, so let's look at what we got. So what we know is what? Pardon me. The ideal gas law. Right? So from the ideal gas law, what we know is that for part A, we have the pressure times the volume is equal to what? The number of molecules times kb times T. Right? So in this case, we want to know per molecule. So we're looking for this particular value. So from here, we can solve for N over V. So this is going to give me then that N divided by V then is equal to what? So in this case, I'm dividing K, dividing that over here. So it's going to be the pressure divided by Boltzmann's constant times the temperature. So in this case, we know this. We just have to put this into pascals, which is multiplicative change. This is already in array units. So if I plug this in, what I get in this case then is that there works out to be about 3.27 times 10 to the 16th molecules per meter cubed, which if I convert into centimeters, then this is the same thing then as 3.27 times 10 to the 20th per centimeter cubed. Oh, sorry, to the 10th per centimeter cubed. There we go. Yeah, because there's a 10 to the 6th difference. Great. So part B then, we can then find the mean free path. So the mean free path then is going to be, again, 1 over the square root of 2 times pi times d squared times n over v. Well, we now know n over v. We know d, that's given to us in the problem. So in this case, what we find is that this works out to be about 172 meters. So at this particular temperature and pressure, we find then is that the average distance between two successive collisions for this particular ideal gas is about 172 meters from one collision to another collision, which is a pretty good distance. So it's almost 2 football fields worth of distance before these guys actually collide with another particle. So this is mean free path.